All right, so asynchronous session, CS255. Our topic today is routing protocols. All right, so we just finished our network layer discussion, and we learned the network layer itself provides us end-to-end delivery of our messages, um, and it does so by the use of multiple routers. So specifically, those routers themselves allow us to group together various machines that can have totally different hardware using a value called a IP address, which identifies the network. And specifically, on a high level, how our messages get delivered is when a message itself arrives from the transport layer. It could be something like a TCP segment or a UDP datagram. Our machine, okay, attaches a network layer header to it, which could be a IPv4 header or IPv6 header. This header contains things like the source IP address, destination IP address, and again, depending on the header that you choose, various other fields. When the message arrives at each intermediate router, that router itself inspects the destination IP address, and it uses the prefix system that we discussed in order to get our message closer and closer to the final network. Okay, and so as an example, the prefix system that we discussed, it provides this organizational system for networks, such that if we see a IP address with the prefix, let's say 00000011, if we see this specific prefix as a bit string, we can see that this number evaluates to 3, which we should know means that this belongs to Amazon Web Services, AWS. Okay, and you can, so this is, of course, the largest, but you can imagine some other bit string to represent CUNY's network, and another bit string would represent NYU's network. Okay, and those would probably be much longer. Okay, but again, the prefix identifies the network, and then that network itself can have a certain number of hosts. Right. So our prefix system identifies networks. And so all we really have to do if we see this prefix is get the message to one of AWS's servers. Okay? So what we essentially skipped over last week was the how. Okay, and that's what we're going to be focusing on in today's class. That is, when a message itself arrives on a router, let's say R1, and let's say that the final destination is for some network F. Okay, I need to get it to that network F, and R1 itself has to make a decision between R2 and R3. Okay? It has to make a decision. Where do I send this to? And let's say that both R2 and R3 eventually connect to F. Okay, there might be 5 routers in the middle of here, 4 routers over here, but they're high speed. So the question really is, how does R1 decide between sending the message to R2 and to R3? That's what we skipped over last class. We essentially said that there was some magic box that R1 used to figure out how to send it to R2 or to R3. And that's what we're going to be looking at today. That is essentially the essence of the routing protocols, which are essentially algorithms that dictate the path messages will take to get to their final destination. So in fact, let me write that. That's fine. So algorithms that dictate the path messages will take to get to their final destination. Okay, so with regard to routing protocols, they fall into two major categories. We have exterior gateway protocols, EGPs, and we have interior gateway protocols, IGPs. And the difference between the two is exterior gateway protocols communicate between different autonomous systems. So they facilitate communications between two or more autonomous systems, which I'll abbreviate AS. Whereas IGPs facilitate communication inside of a single autonomous system. So we got to define this word, autonomous system. Communication inside of a single, and let me spell it here, autonomous system. Okay, so for autonomous system, we need to find that. We need to define two words. So we need to first define network operator. So network operator is easy enough. It is the owner of a network, the person who's in charge of all devices within a network. For example, for my home network, I am the network operator, and probably for your home network, you are the network operator. For Queens College, there's probably a Office of IT that is the network operator for the Queens College network. So this is the owner of a network. Okay. And then we have autonomous system. Okay. Which are network operators that facilitate the delivery of messages across the internet. In fact, I should put large here. Large network operators that facilitate delivery of messages across the internet. So your ISPs typically. But there are other ones, including just internet backbone companies like Cloudflare. Across the internet. Okay, so in fact, let me sort of bring up a picture. Right, so very often people sort of think like the internet sort of looks like this, where we have sort of all these independent routers out there between our client and some server, and this is maybe slightly appropriate for the early internet, but nowadays everything is much more clustered into very large organizations. So it's much more closer to something like this, where you have these very large ISPs like AT&T, Verizon, Sprint, and so on, which are connected to websites and universities. That is, it's much more condensed than you would think. There are not that many actors out there in terms of autonomous systems, and for the most part, these autonomous systems know each other. Okay, because they're constantly delivering messages on behalf of their users to each other, and they keep each other up to date with the IP addresses the range of IP addresses that they own. So usually it's easy to deliver messages between different ISPs. Now, if an ISP ever gets a message that it doesn't recognize, there are solutions. We have IANA, who manages all the IP addresses, and they break it up into different geolocated blocks. For instance, Aaron is in charge of all the IP addresses in North America, and they have a specific multiple IPv4 blocks of IP addresses. So even if you don't really know the IP address and you send it to your ISP, if they don't know it, they can always check to see if Aaron knows it, if it has a prefix that begins with the North American range, and there's one for every continent. So you can get by pigeonholed, you can guarantee that even if you don't know this IP address, I can get it to one of these entities who knows who I can continue to search for. Okay. So why do we have two different protocols? Why do we have EGPs and IGPs? Well, the main reason that we have two different protocols is EGPs require this notion of trust. That is, if I give you a message, okay, let's say that I have a customer or something. If I give you a message, how can I be sure that you're going to deliver it? Okay, if I forward, even if it's encrypted, you can't read it or anything, how can I be guaranteed that you just don't throw away the message? In fact, why would you? Let's say that you have 100 of your own customers, you're some ISP, you can only support, let's say, 105 customers, and you have 100 customers. So essentially you have very little leeway. You have maybe 5 customers worth of additional bandwidth. And why should you use that extra bandwidth on network that is not a customer of yours. Okay? That is, if why should I facilitate traffic for someone else? This notion of trust. Um, and so, what stops one of these entities from just saying, all right, I'll throw away your message? Okay, just take your message and then just fail to deliver it. Now, in tier gateway protocols, if we're inside of a single autonomous system, that means there is a single network operator, there's a single entity or company that owns the network. And they control all aspects of that network. Okay? And so this notion of trust no longer is necessary. I don't need to worry about trusting myself. So with IGPs, we have the benefit of we can ignore trusts and we can just focus on the wider issue of getting our messages to closer to our final destination as fast as possible. We can focus on the notion of speed. And so our main focus in this class will be IGPs, but we will touch briefly on EGPs, just maybe 10, 15 minutes or so, to just sort of talk about them. Okay, and EGPs are actually very interesting in that most of their solutions are in terms of contracts and business agreements. Actually, turns out the best way to establish trust and ensure that your messages are delivered is to have a lawyer behind you. Okay, but let's talk about some types of exterior gateway protocol relationships. Okay, so let's say that we have two ISPs. Let's say we have two large ISPs. Let's say AT&T and Verizon. Okay, so these are two very large multinational ISPs, and they have lots of customers. Let's say customer 1, customer 2, customer 3, and customer 4. And because they are large companies, they are very tightly coupled with each other. AT&T knows Verizon's network, Verizon knows AT&T's, at least their edge network. Okay? And so the easiest scenario that both of the companies would love is if customer 1 only wants to communicate with customer 2. They only want to communicate with each other, then this is easy because both customer 1 and customer 2 are giving money to AT&T, and so AT&T has this vetted interest in delivering their messages to each other. Okay? Now, if, let's say, customer 1 wants to send a message to customer 3, now we have an issue in that customer 1 is a customer of AT&T, but they are not a customer of Verizon. And one of the key things that is important to sort of understand the reasoning for this is that infrastructure is not free. Infrastructure is not free. In fact, it's fairly expensive. It's not free. And any infrastructure spent delivering C1's message, okay, for AT&T, is infrastructure that is not being used to facilitate Verizon's direct customers, okay? And so Verizon itself has a vetted interest in ensuring that their customers are happy, okay? And they will avoid, when possible, causing their customers congestion, Now, in this particular scenario, customer 1 wants to communicate with one of Verizon's customers. Okay? And the assumption here is that the Verizon's customer wants to, in fact, communicate with one of AT&T's customers. So Verizon will allow this traffic. Okay, Verizon will allow this traffic because one of its customers is using this traffic. Okay, it's using this traffic as well. And they have a vetted interest in ensuring that C3 gets a good experience as well. So this type of relationship, if we extend it, okay, in that AT&T on a per customer basis has roughly as many customers who want to talk to Verizon as Verizon on a per customer basis has people who want to talk with AT&T relatively. Okay, it's proportional to the number of customers. If one side has a lot more customers, percentage-wise, those customers are probably talking to AT&T just as likely as AT&T customers are talking to Verizon. So this type of relationship where essentially Verizon says, I'll deliver your messages if you deliver mine, is called a peering agreement. And it works best, when the percentage of traffic that one side is sending to the other is about equal. Okay. So in this type of scenario, Verizon and AT&T will draft up some contract. They'll say, hey, I'll deliver your messages if you deliver mine. And because we have roughly the same amount of customers who want to communicate with each other, this is something that we can do without exchanging any money at all. Okay? Easy enough. Now, the peering relationship doesn't work in all scenarios. Okay? So let's say again that we have AT&T and we have Verizon. And again, we have customers C1, C2, C3, and C4. Okay, so these are all customers of the ISPs. Now let's imagine that there is a large company out there. Company, we'll call it X. Okay, company X is very large. And company X itself is a platform that delivers a lot of content. Okay, deliver a lot of content. And some of AT&T's customers also, and some of Verizon's customers also subscribe to Company X's services. They are a customer of not just Verizon, but also Company X. Company X is not an ISP. They are a content provider. Okay? And so when a request is made, okay, let's say customer 2 says something like, download this file, okay? This message itself hits Company X. And so this request might be a couple of bytes. It's just like a click or something for something that you want to download. So maybe AT&T is putting onto Company X's network a few bytes at most. Just representing the file that they want to download or something. And then the reverse happens in that now, once the request is made for that particular file, company X sees that C2 is their customer and is going to say, all right, you want this giant movie? Here you go. Here is that giant movie. And all of a sudden, company X is putting several terabytes of data onto AT&T's infrastructure. Let's say this movie is 1 terabyte large. Okay, and so this is putting some stress onto AT&T's network. And the problem is that customer 2 is very happy. Okay, customer 2 is getting the content that they wanted. The problem is if we have a lot of people like customer 2, then those who are not subscribed to company X, like customer 1, have a degraded experience. Okay, customers 1 and customer 2 do not have as good of an experience because all of the cables on AT&T and Verizon's networks are being saturated by company X's data. Okay, and again, we mentioned this, but infrastructure is not free. Okay, it costs money to put cables in the ground. It costs money to build radio towers for cellular networks. All of this is very expensive, and it's very expensive to expand. And so if you have one particular company, okay, that is saturating your network and you're making the experience much worse for everyone else because, of course, infrastructure is not infinite, then we have a problem. And in fact, this was a very big sort of historical story several years ago. And this company, which you may have guessed by now, was on the news. So this company X is actually Netflix. That is, Netflix had many customers, okay, that were using Verizon and AT&T, and they were shoving so much data onto these networks infrastructure that it saturated their entire network, and it made the experience for everyone else who was not a Netflix customer that much worse. And so what happened after a very long legal battle was that Netflix eventually agreed to use a transit relationship. So a transit relationship. Which is where Netflix itself and similar companies that are in this sort of very one-sided message delivery way agreed to pay ISPs like AT&T and Verizon some money to expand their infrastructure. So in this case, a autonomous system will pay to have their messages delivered. Okay, so this is the other type of relationship, the transit relationship. And so you can sort of see that EGPs in general, essentially what they mainly focus on are sort of rule systems, okay, that is, which networks do I have peering agreements with? Which networks do I have transit agreements with? Which networks do I consider bad actors? I don't want to communicate at all. Which networks can I use for free? There might be some networks that just say, yeah, you could put any data that you want through me. I trust your network or something. If you have these types of relationships, then and a lot of it is more business than computer science, in my opinion. Okay. And so we don't really need to discuss it further than that. And instead, we will focus on the IGPs now, okay? Which is where most of the lecture is going to be. So we're going to focus on the interior gateway protocols. Protocols or IGPs. And the goal here is much more simple because the goal with EGPs can be complex. You might have a company who is solely oriented on maximizing profits, and so they want to have the maximum number of transit agreements when they are the one that is facilitating the delivery messages, and they might want to have the least amount. They might want to use peering in scenarios where they are sending out messages. Okay, or maybe they get all their money from their customers and they're solely focused on speed, or they have some type of hybrid, or maybe something else entirely. You can optimize in various different ways. You might want to optimize on trust. That is, I want to choose the network that I trust the most to deliver my messages because these are very important messages that need to be delivered. Now, with IGPs, because we're internal to a single network, we don't have this notion of trusts. Okay, we don't have to worry about trust because I am the owner of the entire network, which means that I'm also the owner of every router along the network. And so my goal changes in that my goal simplifies to just get to the final destination as fast as possible. So our goal becomes just end-to-end delivery, end-to-end delivery as fast as possible. Okay. And in fact, maybe end-to-end is not the best word for this. That is, we're not really getting to I mean, technically we could be, but let's see. Oh, there it is. What's a better phrase? So we want to get to the sort of end of the network. So intra-domain delivery. I guess it's intra-domain. Intra-network. Intra-network. That is, we're inside of a single autonomous system. Even I guess it's fine. Intranetwork. Although some autonomous systems, I should make a caveat. Some or most autonomous systems contain many networks. So most autonomous systems contain many networks. Okay, but our solution, our main problem anyways is that we want to get to our final destination as fast as possible. That is, let's say that this is our autonomous system. Let's say this is our Verizon autonomous system. Okay, and each of these circles represents various networks with maybe hundreds of computers inside of them. And we want to get to this location. Let's say here's where we start, here's where we end. And we want to find the shortest path to that end destination. Now that end destination might not be the actual end destination because we might have to go to a different network or a different AS in order to maybe AT&T's AS, okay, in order to get to our final destination eventually. Okay, maybe this is our final destination. And so in this case, we do need to use an EGP protocol because we're communicating between two different networks, and we need to ensure that AT&T itself makes our final delivery. Now in this case, they probably do want to, okay, and that's they have a customer who wants that message delivered probably, but it could be a scenario where AT&T is just a middleman. Okay, it could be another autonomous system down here. That could be the actual final destination. And then in this case, there's a chance AT&T, if they don't have a relationship, will say something like, go find a different path. Okay, you're not my customer. You don't have any agreements with me. I don't trust you at all. Go find a different path through some other EGP to get to your final destination. Okay, so our main focus will be inside of a single autonomous system, because we're inside of here, we control all the devices, which means that we don't have to worry about trust, and we can just focus solely on speed. Okay, and so when we focus just on speed, the problem becomes much more familiar. That is, we are essentially trying to get from some starting destination to some end destination as fast as possible. And so this problem, or at least a variant of it, you have looked at. Okay, the problem that we're of course discussing is the shortest path problem. And the solution that you learned inside of CS313 is Dijkstra's algorithm. Okay, although Dijkstra is actually not the solution to the shortest path problem. It does not solve this. What Dijkstra solves is a very special instance of the shortest path problem. What Dijkstra solves is what we call the single source shortest path problem. Okay, so there's a variant of the shortest path problem called the single source shortest path problem, okay, which Dijkstra solves. In that if you feed it, so the difference is as follows, in that if you have a implementation of Dijkstra, let's have some function, it'll always have three parameters. Always three parameters. It'll have the graph that you want to feed it in, the starting location, the starting node, and the end notion, the end node. Okay, and so this is what single source stands for. Stands for this starting node. It says that giving a starting node and an end node, I will find you the shortest path between starting and end using this graph. Okay, now this might seem like a very nuanced difference, but for the pure, for the version of the shortest path problem that is not single source, for the actual shortest path problem, so for the actual shortest path problem, there is a different algorithm, shortest path, which we'll be looking at, called Bellman Ford. Which I'll abbreviate BF, which takes as its input just a graph. Okay, and so now this is very interesting in that Dijkstra requires 3 inputs, Bellman Ford requires just 1. And so with Dijkstra, you feed it the graph, the starting node, and the end node, and it'll give you the shortest path from S to E. Okay? Now, with Bellman Ford, I don't feed it either S or E. Okay? I don't feed it S or E, but it still gives me the shortest path. And so my question would be, which shortest path does it give me? Okay? Now, the absolute shortest path inside this graph is actually completely useless. I don't care about that. It would just be whatever the smallest edge is. Okay, we wouldn't need an actual algorithm for that. Just find the smallest number. And so that's not what it does. It gives us, in fact, what it gives us is it gives us every shortest path. So it gives us, for every pairing of nodes inside of graph G, it will give us the shortest path for that pairing. Okay? So this is a much more powerful algorithm, and in fact, it fits the name much better, and that gives us every shortest path. Okay? Whereas with Dijkstra, its name is, the problem that it solves is not shortest path, but single source shortest path, in that you have to give it a starting location and a ending location, in fact, as well. Okay? And it will find you the shortest path from S to E. Okay, so before we go further, so Dijkstra was covered inside of your CS313 course, but I will do one example. Okay, we will do one example of Dijkstra just as a refresher. Okay, to ensure that you are still familiar with the problems. Okay, so we need to start off with our node S and our node E at the end. Okay, start and end. And let's add some intermediate nodes, A, B, C. And we need 3 more, D, E, F. Actually, we can't use E. So we will do, let's do X, Y, Z. And I'm going to put some weights on these. Let's do 1, 2, 4, 2, 5, 1, and 10, 1, 4. Okay, so we want to find the shortest path from S to E. If we just eyeball it, this one is 13, this one is 8, and this one is 9. So SBYE is the shortest path from S to E, but we're going to run through the actual algorithm so that we do it properly. Okay, of course we can't eyeball a graph when it's 50 nodes and 1,000 edges or something. Okay, but it does help us sort of see if we're going in the right direction. That is, our end result should be SBYE. Okay, so Dijkstra, it uses a special data structure, okay, in order to facilitate delivery, and that special data structure is the priority queue. Okay, so Dijkstra uses a priority queue, and the priority queue, the main feature of the priority queue is that we can insert. So priority queue we can pop off from the top, but we can insert into the priority queue at any location. Okay, we can insert additional data at any spot. All right, So typically how this goes first is we put inside of the priority queue, we put inside of priority queue S and sort of the total cost that we have so far. So in this case, it would be S and 0 because we haven't moved at all. And what happens is that at each step, we do something called relaxation. Relaxation occurs when we take the first element at the very top of our priority queue and we essentially expand all unopened edges, and we put the node that we can reach into our priority queue after removing after removing that element, okay, and consuming it. So essentially we consume this element and we add A1, B2, and C4 to our priority queue. And of course we order them from smallest to largest. Okay, so that's what we're going to do. Let's see. All right, so first we are essentially going to consume this. And then we are going to add to our table A1, B2, and C4. Okay, so these pairings have been added to our table. At this point, we are going to relax the topmost elements. Okay, so again, because I can't select it. Okay, so we're going to relax A at this point. So that's going to include, I'm going to expand down to essentially X over here. Okay. In fact, I guess this is fine, yeah. So we'll expand down to X. And so because A has been consumed, we can remove it. Okay. I could probably, yeah, just do that. There you go. Yeah, perfect. Okay. All right. So A is consumed, and we get X. X, the total cost now is 2 plus 1 is 3. And so X will go in between here. X and 3. Okay. Next, we expand the topmost elements, which in this case is B and 2. So essentially, we're saying that, hey, going further down here is expensive. Maybe this will get me to my final destination faster. Maybe this one will get me to my final destination. So I'm going to expand that down that one. So we consume B2. So we consume B2. Okay, and we expand it. Oops. There you go. And we expand it. Which unveils y. Okay. And our total cost would be 5 plus 2 is 7. So we can put y 7 here. Okay. And again, you can sort of see that we're inserting in a way such that the smallest number is always on top. And so now we see that this going down this path was a bust. And we're going to go back. Going to go back to X. Okay, so our next consumption element is we're going to consume x3. So we're going to consume x3. And so consuming x3 opens up our final destination, E with a cost of 13. Okay. And so if this ever bubbles up to the top, okay, if this ever bubbles up to the top, that means that this is the shortest path. But if something else reaches E before this one does, then it means that this one is not the shortest path. Okay, so next we continue on. We found a path, but we don't know if it's the shortest path. So we continue on. Our next element is C4. Okay, so we go to C4, and we are going to expand out. We're going to expand out this one, C4. Okay, so we're going to expand out C4. And so we learn about Z5. Okay, so we learn about Z5. Okay, which also becomes the next one that we consume. So we consume Z5 immediately because it is the cheapest. And that unlocks E with a cost of 449. And unlocks E9. Okay. Which makes sense because this is still not the cheapest path. It's better. It's better than the one that we just had. And that we learned about this one as well now. Okay. But we want to finally resolve y7, which gives us our shortest path, SBYE, with a cost of 8. Okay, 2 plus 5 plus 1 is 8. Okay, so this one we add E8. So after removing this one, we add E8, which is the cheapest path. Okay, when we finally resolve this, we get the cost. And we have our path along the way. So that is Dijkstra. And you can sort of see why we need the start and the end for Dijkstra in order to essentially guide us towards our final destination. Now Dijkstra itself is very efficient. It runs in n log n, which is probably as good as you're going to get. Now the issue is that it doesn't work that great for the internet, at least not in its original form. In that, imagined that we had a network, or multiple networks, that looked something like the following. So imagine that we had a cluster of routers. R1, R2, R3, R4, R5. And now, the issue is that if a message arrives at R1, does R1 know the intended destination of this message? At what point, or more specifically, at what point does R1 know about the destination of this message? Okay, that this incoming message, so new message. At what point does R1 know about the destination address of this message? And the answer is when that message arrives. Okay, so at the very last minute, the message arrives at R1, and R1 is finally able to look at that destination IP address. Okay, it's finally able to look at it. And so let's say these are the only options. Let's say that it's R4. Okay, it's a networked on R4. Now, at this point, R1 has to calculate the shortest path from R1, from source R1 to destination R4. And this will take n log n time. Do you see the issue here? In that the issue is that R1, as soon as the message arrives, then you have to add n log n time to it. Okay, so that is the router is doing work after the message arrives. And this is necessary because Dijkstra itself, again, the algorithm requires the graph, the starting node, and the end node. But you don't know either of these. You don't know either of these until it's essentially the very last minute, because that's when the message arrives. Okay? Which means that you can't really pre-compute values. Okay? And this is where Bellman-Ford shines. Bellman-Ford is a much simpler algorithm in that, well, I wouldn't say simpler, but it's very, the input is simpler in that it only requires a graph, and it gives you every shortest path. That is, let's say that R1 needs to get to R4. Okay, it'll know the shortest path for that. Or let's say that R2 needs to get to R5. It will know that one as well because it knows every shortest path. So it knows every shortest path, which makes it much more applicable for the internet because you run Bellman-Ford every now and then in order to keep your tables refreshed. Whereas with Dijkstra, as soon as the message arrives, you need to pay that n log n. And then another issue with Dijkstra is you can't forward that information down to the next router. The internet layer frame doesn't contain that information. And so that information about the entire path is lost. And then when we reach R2, R2 has to compute n log n again. And when we reach R4 again, it has to compute n log n. So we sort of have this number of routers times n log n. In that, unless you have some mechanism to embed the entire path that R1 discovered into the frame, then R2 is going to have to recalculate everything. Okay, so we are going to next talk about Bellman-Ford. Okay. So Bellman-Ford itself is an algorithm that solves the shortest path problem. So it's a solution for the shortest path problem. Okay, so the shortest path problem is this theoretical computer science graph problem which uses a theoretical computer science algorithm to solve. Um, Now, what we'll be looking at is not the Bellman-Ford algorithm itself, just because it's very similar to what we actually want to learn, and doesn't make sense to sort of teach it twice, which is distance vector. Okay, so distance vector is an implementation of Bellman-Ford. It is a network algorithm. It's a network routing algorithm, in that it helps networks find the shortest path to each other. Okay, it helps find the shortest path. The main difference is that Bellman-Ford itself is this theoretical computer science graph problem type algorithm, and distance vector is a implemented networking algorithm. So this is like in sort of theory versus application type scenario. There are some other differences as well. Bellman-Ford works as a single actor, whereas distance vector itself is distributed. It is a distributed algorithm, in that whereas in Bellman-Ford you have one central CPU who essentially enumerates all the nodes in the graph. With distance vector you have many routers. Okay, you have several routers that are all sharing their tables with neighboring routers, so they all act sort of independently, sharing information in order to get a view of the entire network, of how the entire network works. So that's one of sort of major differences, that distance vector is this distributed algorithm. Another asset for Bellman-Ford is that, so Bellman-Ford and distance vector both operate at big O of n squared. That is quadratic. And this is slower than Dijkstra. But it's important to note that, again, Dijkstra and Bellman-Ford solve very different problems. Dijkstra solves the single source shortest path. That is, you need to know the ending node. Okay, so you need to know, so specifically you need to know the ending node. Okay, and the problem with that, so with normal graph problems that's not a big deal, but the problem with that in the internet application is when you receive a new message, okay, like when you receive a new message, it's only at the point that the message arrives on the router do you know the ending node. Which means that you cannot run this algorithm until the message arrives. Which means you pay that n log n cost at the worst possible time, right as you need to figure it out right away. Now in contrast, Bellman-Ford gives you every shortest path when you feed it the graph. So meaning that I can pre-compute this values. I can have R1 feed it the graph of the world that I have, and then when this message arrives at R1, well, R1, because it ran Bellman-Ford, knows every shortest path, and so it's just a very simple lookup in order to get to R2, R3, R4, R5. It's just a lookup inside of a table because I've already done all the heavy lifting. We can pre-compute these values. Okay, and then when a message arrives, it's just a lookup. Oh, you're trying to get to R4? No problem, look it up. In contrast, over here, we won't have those values when the new message arrives. Okay, the new message arrives with R4. Well, let me run Dijkstra on G, S, and R4 now. Okay, and so that is one of the benefits that Bellman-Ford has over Dijkstra, that you can pre-compute these values. Okay, so this n squared doesn't look that bad when you consider that you are only paying this value in the background. In order to actually make the messages, in order to actually forward the messages, it costs you a constant amount of time. Let's look at an example. Okay, so the first example that we're going to look at is a simple network. Let's say A, B, and C. So this is a simple autonomous system composed of 3 networks, A, B, and C. So there's a single central network operator who operates these 3 networks. Okay, let's put some costs on these edges, 1, 2, and 5. And so these are networks, so they represent entire blocks of IP addresses. For example, maybe this is 6.6.0.0/16, so there's 65,000 devices on here. And maybe this one is 7.7.7.0/24, and there's 256 devices on here. And maybe this one's 8.8.0.0/16, so there's 65,000 devices on C. Okay, so these are 3 medium to large sized networks, all administered by a single network operator, and they want to find the shortest path between them. We can clearly see that the shortest path is over here from A to B to C, okay, avoiding that that expensive path, which costs 5. But if this is our first time setting up the network, then these networks have no idea what the shortest path is. Now, internal to each of these networks, so inside of network A, there may be many routers, okay? Those routers can speak with each other. Typically, there's inside of a network, it's usually very fast, okay, because you don't have to traverse long distances. And what happens over time is inside of the network, they build up a unified routing table. Okay, so this routing table is essentially a network's view of the outside world. A network's view of the outside world. Or essentially how much it costs to traverse to different networks. Okay, and so each network has their own routing table. So the routing table is unified, but it's only unified with routers inside of this network. So if we're outside this network, let's say this one is A's routing table, this one is B's routing table, and this one is C's routing table, then they have different routing tables. So we'll call this one C, A, and B. Okay, now this routing table has 3 main columns inside of it. Those 3 columns are network, costs, and next hop. Okay, so network, costs, and next hop. That is, the first column is the destination network that you're trying to get to. The second column is how much it costs to get to that network. And the third hop is who should I forward the message to in order to get to that destination network. As an example, in our finished result, we would like to have something like, if we're at A, okay, and we want to get to C, okay, then we're looking for the cheapest cost is 3, but we use B as our intermediary. That way we forward a message to B to get it to C eventually. Okay, so that's what we're going to look to build. Now initially, we don't know anything. In fact, the only thing that we know is if we're on network A, we know that we exist. Okay, and the cost to get to ourselves is, we'll just say it's 0. And there really is no next hop, but we'll just put ourselves again, just to be consistent. Okay, the same for B. and the same for C. This is all we know initially. Okay. So routing tables, routers, learn about the world by periodically sharing their routing table with their adjacent neighbors. Okay, that is, A will share its information, its routing table, with B and C. B will share its information with A and C. C will share its information with A and B. And through this sharing process, all the networks inside of this autonomous system will eventually converge to know everything about the network. Okay, so we'll start off this by having, let's say inside of our hypothetical example, A shares first. Okay, now the question is, what does A share? Well, this doesn't seem to be much, but A shares what we call a distance vector, and that's where the name of this algorithm comes in. The distance vector itself is composed of the first two columns of this table. Okay, the first two columns of this table. In this case, network and cost. So we have a distance vector that looks like the following: A and 0. Okay, and we're going to send this to B and C. Now, upon B receiving this message, it learns that network A exists. Okay, and it sees that if I can get my message to network A, it can get it to any device on A with a cost of 0. I also learned that the edge cost is 1. Okay, so I add these two values, that is, A can deliver my message to any machine on A with a cost of 0, and I can get to A with a cost of 1, so my total cost is 1. 0 plus 1. Okay, and my next hop is through A to get to it. So one question that may arise is how do you get this value of 1? How does B learn how much it costs to get my message to A? Now, there's a couple of algorithms out there, but the easiest one is just to have B send a message to A that says, send this message back. Okay, and before you send that message out to A, you start a timer. You start a timer. B starts a timer, sends the message out to A sends it back, you stop the timer. Okay, now that gives you an absolute value in seconds, which you can then use to compare with the connection speed of all the other connections that you have to get a relative amount. And that's all that really matters, relative. That is, if this value is 1 and this value is 2, then what it means is roughly there's twice as much latency on the value of 2. The units that we're using here are latency. So the higher the number, the slower the connection is. So you want to minimize, in order to optimize for speed, you want to minimize the value. But in the same regard, if you're comparing, let's say, 2 and 5, then this connection is 2.5 times faster than this connection. Okay? Okay, so B learns about network A that's directly connected with a cost of 1, and its next hop is A if it wants to get a message to. This message that's sent out is also sent to C. And so C gets it, it learns about A. Okay, it learns about A, and this time it takes this value 0, it adds this edge cost of 5 to it. Okay, so I can get to A, I can forward my messages to A with a cost of 5. Okay, now this is not the shortest path. The shortest path is here, but we are not done yet. Bellman 4 distance vector is this iterative algorithm where over time we learn the shortest path. Okay, but the nice thing about it is that very quickly we get a path. We might not get the shortest path, but we get a path right away, which means that, let's say that at this exact moment, a message arrives. Okay, a message arrives, and it has destination address 6.6.2.2. Okay, and so we do our prefix matching to see 6.6. It matches network A. Okay, it matches network A. And so we will forward our message out on this edge to get our message to A. So it works very quickly. Like it gets set up very quickly. And over time, it will find the better path and it will update these values um, appropriately. But you can sort of see that we can use our prefix matching already to see that this is network A is over here, and we're forwarding our message to A right away. So we can sort of start, it starts working very, very quickly, even if it's not the best results. Okay, so let's move. All right, so A5A. All right, so A has finished sharing. Okay, let's get rid of this. Okay, A is finished sharing, and now the order in which the tables share is not guaranteed. They operates on their own clocks. It's this distributed algorithm. For example, I believe a implementation of distance vector RIP uses a timer of 30 seconds between routing table exchanges. Okay, but again, they can fall out of sync, and so the order itself is not guaranteed. During your examinations, I will tell you the order that we're going to be using. But in this example, just to highlight that, let's say that instead of B sharing next, let's say that C shares next. C shares its routing table. So now C has learned something already. Okay, C has learned about A, so that is now part of its routing table. And so its routing table now, its distance vector, now looks like CA05. Okay, and this is sent out to C's neighbors, which are A and B. Okay, so let's start with A. So A receives this. It learns about C with a cost of 0 plus this edge cost of 5. Okay, it's directly connected, 5. Now it has this value of 5 as well, which we add 5 becomes 10. So we have A 10 through C over here. But of course, this is just like a loop, and I would never use this path. A would never use this path because you can get to A without going through C. So if a value itself is ever larger than a value that you already have, then you just ignore it. You throw it out. Okay, so we're not going to use that path. Now this same distance vector also arrives on B. Okay, so B learns about C. Okay, learns about C with a cost of 0 plus the edge cost of 2. So it has a total cost of 2 through C. That is, B can get to C with a cost of 2, and then C can get to C with a cost of 0. Okay, and we also have this one over here, A5, and this is essentially saying that, hey, if you get your message to me, C, I can get your message to A with a cost of 5. Okay, so that's going to be 2 plus 5, it's going to be 7. Okay, so it's going to be A 7 through C. Now, of course, we have a much cheaper path over here, and there's no point in using this path that costs 7 when there's a path that costs 1. So again, we ignore this path, we throw it out. Okay, so we're done with this one. Finally, it is B's turn to share distance vectors. Okay, so B's distance vector would be BAC 0, 1, 2. Okay, and so B is going to share this with its neighbors A and C, of course. So we'll start off with A. So A learns about B. Okay, learns about B with a cost of 0 plus 1, this 1, through B directly. Okay, it learns about A with a cost of 1 plus 1, 2, but it already has 0 over here, so we can ignore it. And then it learns about C with a cost of 2 plus 1, which is 3, okay, we have a cost of 5 over here through C, which is this link. And so what essentially A is learning is that if A gives its message to B instead, B can deliver it on behalf of A with a cost of 2, and it costs 1 to get it to B, which means that total cost is 3. It's 2 plus 1, 3. And that value is cheaper than the existing 5. So we're going to replace this with 3. We're going to replace this C with B. Okay, so instead of sending it to C, we send it to B as our next hop. We still get to C at the end, okay, but we found the cheaper path. Okay, so that is done with this one. Next, we move on to C. C also receives this. Okay, so first, we'll start from the top. C learns about B with a cost of 0 plus 2. Okay, next is A, which we have 1 plus 2 is 3. We have 5 here, so we're going to replace this 5 with 3, and instead of using A, we now use B as our intermediary. Okay, we still get to A, of course, it's just that we're using this path. And now, again, if a message arrives on C, okay, if a new message arrives on C with the destination address 6.6.2.2, let's use the same address, okay? Well, now we look up the network that matches this prefix 6.6.2.2. Okay, we see it's A. Okay, this is the prefix that matches. And this time, instead of sending it to A, we send it to B. Okay, we send it to B because we know a cheaper path. That is the benefits of Bellman 4, that we can operate very quickly, and then over time, we will converge. All these tables will converge into seeing the world in the shortest path possible. That is, at this point, we have the shortest path in all the tables. Now, this is the type of problem that you will get during your examinations. This is a simplified version of what actually happens. What we'll do next is the actual implementation. And the reason why the actual implementation is more difficult than this, there's a flaw with this diagram. The flaw with this diagram is that the numbers over here, so with networks, with actual networks that you use, it's possible that edge costs go up and down, that they change, okay? And this type of table that we're using, this one-dimensional table, only allows the numbers to go down. They can get cheaper, okay? They can get cheaper and it still works. But as soon as they get more expensive, it fails. That is, let's say that this edge, okay, suddenly becomes much more expensive. Let's say it becomes a cost of 4, okay? Now, A and B, they both realize this. Okay, A and B both realize this. And so they will update their numbers accordingly. Okay, so, right, so the limitation for this one-dimensional table example is that essentially it doesn't remember any of its past information. Okay, it doesn't remember any of its past information. So it doesn't really work well when edge costs suddenly go up. Okay, so imagine that, again, we had this edge cost go up to 4, and both A and B update their tables because they realize it, and then they advertise that this cost has been bumped up to 4. They advertise a distance vector that has a 4 inside of it. Now, C itself is trained such that if it receives a value that is higher than a value that it already has, then it's just going to ignore it. Okay? And so when it gets a value, um, let's say B advertises 4 to get to A, well, C over here is going to say, no, I prefer the existing value of 3. Okay? And that is problematic. Okay? And that the values don't go down. They don't have any mechanism for it to go down. And so the two-dimensional example solves this. But before we look at that one, I want to preface it. We need to look at the Bellman-Ford equation. Okay, so this is the Bellman-Ford equation, and essentially it acts as an Ford equation. It acts as the driver for distance vector and similar algorithms. And so I'm going to define some of the elements inside of there. So the first one that we're going to define is dxy. Okay, so dxy is the distance from, in fact, it is the shortest path. The distance of the shortest path from x to y. Okay, so distance of shortest path from x to y. And so that value is, so first we have this min value over here. So this is a min function. Okay, find the smallest vertice. So min v essentially is saying the collection v is, these are the vertices, collection of vertices adjacent to x. Okay, so it's a collection of vertices that are adjacent to our node x. And then we have 2 more values. So we're choosing the vertex that minimizes this function. Okay, this function itself is composed of 2 elements, c x comma v. This one's the easier one. This is just a representation of edge costs. So this is the direct edge costs. And then we have dvy. And this one looks very familiar because we just saw it over here. If this dxy is the distance of the shortest path from x to y, then dvy is the distance of the shortest path from v to y. It's a sort of recursive definition. Distance of the shortest path from v to y. Okay, so we've got our definitions out of the way. Let's sort of piece it together to see how this works. So let's look at an example. So let's say that we have x and we have a y. Okay, so we have 2 points and we want to find the shortest path from x to y. And so along the way, there can be several nodes. Let's say that we have a node over here. We'll call this v1. We have another node over here. We'll call this v2. We have a bunch more nodes. And then let's say we have some final one, vn. Okay. This collection of nodes, let's say that these are connected. Okay, and let's say that there's more than 3. Okay, let's say that there's a bunch in between. This collection of nodes represents V. Okay, this is the collection of vertices adjacent to x. And so let's give these some, as an example, let's get rid of these for now, and instead we can give these some costs just to make it simpler. Okay, so just imagine that there's a bunch of them, but in this scenario we'll just stick with 3. So we'll say 20 for this one. Actually, let's do 2, 3, 18. Okay, and then out of here, let's say that we have another node, and then a third one to make our connection. Let's say our cost over here is 20, 1. Over here, let's say that we have one node that costs 5, and then we fork, and we have one that costs 1 here, we have one that costs 2 here, and then we have, eventually we get to y, but it costs us a lot, it costs 40, and this one down here costs us 10. As for Vn, Vn has a very crazy path. It's got 3, and then it branches off into a bunch of different things before slowly consolidating back, and then eventually hitting y. And I'm just going to put some numbers here, but the numbers don't really matter that much. We're going to be able to optimize all this stuff away. Yeah, these numbers don't matter on the bottom. Okay, so let's step through this example to sort of try to explain this Bellman-Ford equation. Okay, so our goal to find the shortest distance from x to y, okay, so our goal to find the shortest distance x to y is to choose the v, choose v. Over here we have 3 choices, but you can imagine that in a different example we can have a lot more than 3 choices. Choose v such that we minimize this formula. Okay? So the first part of the formula is c of x comma v, the direct edge cost from x to v. So it's referring to this edge cost, these edge costs, these direct edge costs, which again, this is why this is the easy part of the formula. Okay? So it's just referring to those individual edge costs. So we just take that as essentially a constant. And then we have the recursive definition. That is, essentially what you're saying is you take one step, okay, you take one step to v1, and then you solve from v1 to y recursively. Okay, you solve from v1 to y recursively. And so you're solving this problem now, the shortest path from this one. And you repeat it for all the other edges, and then you choose the one that gives you the smallest number. Okay, it's very so it's very greedy in that aspect, and that it's just going down the path. So let's step through how this would work. Okay, so let's say that, so in our first version we have dxy, okay, dxy, that's equal to the min, okay, and now we have 3 choices, okay, and we're going to be expanding all 3 of those choices. So the first one is v1, but then we're also going to do v2 and vn, okay. So we'll start with v1. Okay, so for v1, we're going to do c of x comma v, c of x comma v1. okay, which is, in this case, 2. Okay, so that one we can just very quickly just sub in 2, okay, plus d of vy. Okay, so now we are recursively solving for v1. So we're recursively solving for this problem. Okay, but these are easy because there's only one possible choices, so it boils down to just so it just becomes this element. Okay, so we do C of v1 comma, let's call this v11. Okay, so this one would be v11. Okay, which is 20. Okay, plus our recursive value. Let's get this out of the way. Get this out of the way too. Okay, plus our recursive value, which in this case would be so in fact, let me be consistent a bit about this. I want to be consistent about this. Okay, so we have C of x comma v1 plus d of v1 parentheses y. Okay, d of v1 y says starting from v1 get to y. That is composed of two components, c of v1 comma v11 plus d of v11 y, where v11 is the next step over. Okay, this is 20. Okay, v1 to v11. Okay, and then this recursive value d of v11 y is let's see, this value is v11 is c of v1 v11 comma y. Okay, that's the direct edge costs, plus d of y to y. Okay, so this is 1. Okay, so we have 1 over here. And how much does it cost to get to y from y? It costs nothing, so we are done. Okay, and so the total cost here is, we could just add the edges, 2 plus 20 plus 1. So we get 23. Okay, now of course you could have just added the edges up, but going through this process is going to be helpful because we're going to do the same process, and this time there's a fork. Okay, so for v1, which was the sort of easy one, the answer is 23. Okay, and so all of this collapses down into 23. Okay, so let's move on to v2. v2, we have a fork. Let me zoom out a bit. So v2, we have a fork, and so that makes things a little bit more difficult, but not that much more difficult. So again, we are now doing c of x comma, in this case v2, okay, plus d of v2 y. This one becomes 3, okay, and dv2y becomes c of v2, let's call this v21, we'll call this one V211 and V212. Okay, so we'll use that as our notation. So C of V2 comma V21, okay, so from here to here, plus D of V21 y. This one becomes 5. Okay, that one becomes 5. And V21 recurses down. V21. And this time we have to use that min formula again. Okay, we have to use that min formula again. So this one breaks down into 2 more subproblems. Okay, we break into 2 more problems. One where we go to 211 and one where we go to 212. And we choose, so the first one is if we choose 211. Okay, so it becomes C of V21 to V211. Okay, and the other one plus the recursive one. And the other one is V21 and V212 plus the recursive V211 y and V212 y. Okay, now this one, this edge cost is 1. Okay, this edge cost is 1. This one over here is 2. So typically we'll choose the smaller one. Okay, but we could sort of see that this is the wrong path because there's this big 40 over here. Okay. Let's see. This dv211, because dv211 resolves to C v211 comma 211 comma y plus dyyy, which we already know is 0. Okay, so that becomes 0. This one is 40. Okay, and then this one resolves to C v212 comma y, which we know is 10. And this one resolves to dyyy, which is 0. Okay, so when we get to here, we have 1 plus 40, so that's 41. Okay, 41, or 2 plus 10, 12. Okay, and so here is our first application of min. Okay, so do you choose 41 or do you choose 12? You choose 12. Okay, we're choosing this path over here. Okay, we're choosing this path. Okay. And going back, we're sort of seeing that we're sort of unfolding our results. So we choose our 12, and then we're going back 12 plus 5 plus 3 yeah, 12 plus 5 plus 3. Okay, so we get 20. Okay, and so we work our way all the way back with this formula, and we get 20. Okay, so 20 for this one, which is better than our 23. So we are going to throw away V1, okay, because we found a cheaper path through here, okay, through this very excruciating search. And then finally, this last one, which looks incredibly painful, but this one's actually the easiest, okay? This one's the easiest, actually, because we start our search, Okay, we start our search over here. Okay, we say, so this is composed of Cx comma V3, okay, which is 18. Okay, so this one's 18. Okay, plus d of Vn, well, I should call it Vn, not V3, Vn, as 18, plus d of Vn, y. This breaks down to, let's call this one Vn1. This breaks down to C of Vn, comma Vn1, plus d of Vn1, y. And then this C breaks down to 3. And the interesting part is, now we have 18 plus 3, that is 21. And we can stop right here. We can stop right here because we have a value of 20 already. No matter what, we are not going to get cheaper if we've already hit 21. So we can stop. 18 plus 3 is 21. We're not going to get cheaper than 20 if we keep on exploring down this path. We do not have negative edges. Okay? At least on the like networking worlds, routers don't have negative edges. Okay? So even though this one looked really, really scary, we never actually reach that scary part. And that's a lot of the benefit, that you can short circuit. Okay? So this Bellman-Ford equation is essentially going to be acting as that driving factor for how we evaluate these tables. So moving on to the two-dimensional table. So we'll go back to that same example. So we had 3 networks inside of an autonomous system. I believe it's 1, 2, and 5. And so this time we're going to have a two-dimensional table. Okay, representing A, B, and C's view of the world. Okay. Okay, and so from A can get to B with a cost of 1. Can get to C with a cost of 5, and it costs nothing to get to itself. B can get to A with a cost of 1. It can get to C with a cost of 2, and it costs nothing to get to itself. And C can get to A with a cost of 5, and get to B with a cost of 2, and it got to itself for 0. So these are all just the direct edges. Okay, and so what's going to happen is that these tables are going to share their distance vectors with each other. Okay, they're going to share their distance vectors with each other, and then they're going to apply Bellman-Ford to those results. Okay, so let's start with one sharing of tables. Let's say that B shares its distance vector with A. Okay, so it shares this information, 1, 0, 2. And so what B is saying is that if you can get your information to me, I can get it to you with a cost I can get it to C with a cost of 2. Okay, I can get it to C with a cost of 2. And A knows that I can get to B with a cost of 1. Okay? And so because A knows that it can get to B with a cost of 1, and B can get to C with a cost of 2, then what we can do is we can update this value to be 3. Okay, we can update that value to become 3. In the same regard, if B shares this table, shares its distance vector with C, 1, 0, 2, then C, so we can see that we can get to from B, we can get to A. From B, we can get to C with a cost of 2. Okay. And we can get to A with a cost of 1. Okay. So from C, we can get to B with a cost of 2. And from B, we can get to A with a cost of 1. Okay. And so this, again, means that we should be able to get to C with a cost of 3. Okay, and so these tables are going to be exchanged until all the results converge, and they'll continue to share information. So now that we have a cheaper path over here, we can share that information with each other. You can sort of see that the cheapest path very quickly converges. Now, let's say that one of the edges suddenly gets much more expensive. Let's see, so I think I used 4 in the last example. Okay, so let's say 4. So we need to update A and B. A and B needs to be updated to be 4. So this needs to be updated 4. Choose red. And this also needs to be updated to be 4. Okay, so this needs to be updated 4, this needs to be updated 4, this needs to be updated 4. Now, how these tables push updates that increase the costs is as follows. When B, let's say when B shares its new distance vector, 4, 0, 2, when it shares this distance vector with C, okay, C may not want to update its table because it has a 1 inside of here, okay? But it knows that it has to, okay? And the reason for this is that it knows that this value of 1 is no longer available, okay? You can sort of think about it like the following. You go to a supermarket one day and you see the price of eggs is $3, okay? And then you go to a week later, you go to a different supermarket. Okay, you go to a different supermarket on the other side of town. You see that eggs are $5. Okay, and you say this is too expensive for me. I'm going to go back to my previous supermarket. They were $3. Okay, and so that makes sense. Now let's change the example a bit. Let's say that you went to the same supermarket both times. Okay, instead you went to supermarket A, it was $3. And then 2 weeks later, you went back to supermarket A and you saw it's $5. Now, you can't make that argument saying that I'm going to use a different supermarket that had it for $3 because they were the same supermarket. That option of $3 is no longer there. And so when B advertises that the cost to get to A is 4, essentially C knows that that value of 1 is no longer available. And so it is forced to replace it. So essentially, whenever B advertises, these values will essentially, it'll delete the old values and place in the new values, even if they are more expensive. Okay? And then once it has these new values, it will recompute using the Bellman-Ford equation. It will recompute the table. Okay? And eventually they'll converge. Although this conversion can take a very long amount of time due to things like the count to infinity problem, where it's possible for a value, it's possible for a value to be advertised that uses a intermediate node. Okay, so the typical example for this would be something along the lines of you have 3 nodes, 1, 2, and let's say 50 or something, and then suddenly this connection degrades. So after all the tables have been sort of synchronized, okay, and we have let's A, B, C. So we have something like let's see, A can get to B, A can get to B with a cost of 1, A to get to C with a cost of 50. Whoops. A to get to B, cost of 1, 50, 0. B can get to B to get to A with a cost of 1, B can get to C with a cost of 2, and itself with 0. And for C, it is, to get to A costs 50, to get to B it costs 2, and to get to C it costs 0. Okay, so B can advertise over here 1, 0, 2. Okay, and because we have this and this, okay, we can shrink our costs from 50 down to 3, okay, which can then be advertised across 0, 1, 3. In the same regard, if we advertise over here, then because of because B can get us to A with a cost of 1, and C can get us to B with a cost of 2, this one also can be computed down to 3. Okay, and then this can be advertised out, 3, 2, 0. So, and let me also push these as well. 3, 2, 0, 0, 1, 3. Okay, so we have convergence, and then so the count to infinity problem works like this. One of the edges degrades a lot. Okay, so we need to update this edge. So it goes from 1 to 60. Okay, so it goes all the way up to 60. The same over here. These should be at 60 as well. These these will be at 60. And so one of the issues that can arise is when B advertises this link that costs 60 to C, okay? So we'll update this link to be 60, okay? 60, 0, and 2. Then C will look for a different route, okay? We'll look for a different route that costs less than the 60 from B to A. And due to the residual information that hasn't flowed in from A yet, it may choose a route that based off of previous information. It might use this value like 3 over here, and it'll add, let's see, so instead of going from A to C, which will cost 60 over here, I can choose to go from C to A, not knowing that this C to A path uses B as its intermediary. So it would be something like, all right, I'll just use A instead. That cost me 3. I'm going to add 2 to this value, and it'll be 5. Now, this value doesn't really exist, but it'll be advertised to A. It will be advertised to B and to A that it does exist, and it sort of will go back and forth. It'll advertise 5, then B will add 2 to that and advertise 7, and then C will advertise 9, and we'll essentially climb back and forth until eventually it hits close to 50, in which case there's a cheaper path. This is a very famous problem called the count to infinity problem. And the solution really is that when you send over a path that degrades, instead of sending over a number, you send over a infinity cost. Okay, now force the other side to choose you set the cost of the sender to have an infinite cost, and that will prevent this sort of count. It'll immediately jump up. It's typically called a poison pill. So I think that's all we need to know about routing. The key elements that are going to be important for you. So like this, again, this two-dimensional table is not that important, just because it's too much complexity for me to ask of you. You would typically, if there's anything on the exam regarding this table, regarding routing tables, then it would typically be the one-dimensional example, where I will add a caveat. I'll add an asterisk that say that you may assume that the network costs never only go down, they do not go up, so that you can have the ability to use the much simpler table versus the two-dimensional one, which you can definitely see gets very hairy. It's also very important to understand how the Bellman Ford equation works as a whole, and to work out an example or two yourself. I think that's good. So at this point, you should have a good understanding of how routers essentially make their decision of how to forward, okay, your message such that it gets to your final destination and in the cheapest way possible, the lowest cost. In that, essentially what they're doing is, in the background, they are messaging each other. They're messaging each other constantly every 30 seconds or so, exchanging information about the network. And using that information, they're finding the shortest path to every node, such that when a message arrives, it already knows the shortest path to every other router inside of its interior gateway protocol. So it knows the shortest paths to those routers, and it uses the prefix system of your message. So it sees that your message contains some IP address, let's say 6.6.2.2, and it matches it up with the network that closest matches that. And it'll forward it to that router, the most appropriate router that that matches it the closest and it has the shortest distance to. And this is just a lookup. Okay, so that's the benefit that Bellman Ford has over Dijkstra, in that it's doing this n squared activity, but it's doing it in the background, such that when a message arrives, it's big O of 1 to forward it to the next, to look up where it should go to next and forward it to the next router. Okay, which means that this operates very fast.